as well as the block wave function into the spin up and the spin down state. And then we can individually calculate the Chern number from the spin up wave function and the spin down wave functions. And our results shows that the Chern number from the spin up state and from spin down state equals +1 and -1 respectively. So based on this definition, the total spin-Chern number as well as the Z2 index equals 1. So this result demonstrates that the Hamiltonian model is indeed a quantum spin Hall insulator. And this is the typical process to investigate the topological phase in the topological band theory. If we consider a more complicated situation, we further include the Rashba spin of the coupling and the Zeeman exchange field in the Hamiltonian model. And we'll see that the Rashba spin of the coupling will appear in the off-diagonal turn of the matrix. Therefore, the spin up and the spin down state will mix with each other. So in this case, SZ is no longer a good quantum number. So we cannot decompose the band structure as well as the block wave function into the spin up and the spin down state because the spin mix with each other. As a result, the spin-Chern number cannot be well divided through the block wave function with the spin basis. So it seems to indicate that we have lost our topological invariant number. Here is the spin-Chern number. And we cannot identify whether this system is a quantum spin Hall insulator or not. So in order to solve this problem, we turn our approach from the band theory, band structure, to the feature spectrum topology. And in this case, we project our SZ operator onto the variant state of the Hamiltonian model. So for the case of SZ conserve, before include the Rashba spin of the coupling and the Zeeman exchange field, we find the feature eigenvalue are separated into distinct sectors. The upper sector corresponds to the spin up state and the lower sector corresponds to the spin down state. And because the SZ is conserved in this case, its eigenvalue, h bar over 2, is a constant independent of the wave vector k. So the corresponding feature eigenvalue shows a perfectly flat band as expected. After include the Rashba spin of the coupling and the Zeeman exchange field, the feature spectrum shows a dispersion relation, not a perfectly flat band. Even so, the feature eigenvalue still separated into two distinct sectors. Therefore, we can take the feature eigenstate of these sectors to redefine the topological invariant number and then identify the topological phase transition. Because in this case, we choose the SZ to construct our feature operator. So the Chern number divided by the sectors in the feature spectrum, we still call them spin-Chern number, although this name may not be very precisely. And our calculation shows the Chern number from the spin-up sector and the spin-down sector equals +1 and -1 respectively. So the total spin-Chern number equals 1. So our calculation shows that Hamiltonian model is still a quantum spin Hall insulator, even if we include the Rashba spin of the coupling and the Zeeman exchange field, break the spin rotational symmetry and the time reversal symmetry. And because the topological invariant number is not 0, according to the boundary correspondence, we should have a gapless topological boundary state. However, we find that the original topological boundary state has been open a gap due to the breaking of time reversal symmetry due to the Zeeman exchange field. So this result seems to indicate that the one-to-one correspondence of gapless topological boundary state guaranteed by non-zero topological invariant number is invalid. The answer of this question is reflecting in the feature spectrum rather than the band structure. So this panel is a feature spectrum of this one-dimensional finite size ribbon structure. And we observe a gapless boundary state, this green line, connect the spin-up sector and the spin-down sector in the feature spectrum. And this result just corresponds to the spin-Chern number that we calculated from the bulk feature bands. So next, let me explain the origin of this gapless topological boundary state in the feature spectrum. It's quite simple. The origin of the feature of the gapless boundary state in the feature spectrum can be understood from the evolution of the spin texture on the gapped edge state in the band structure. Let's take a look of this panel. Around the y bar point, we find the spin-up state flip to the spin-down state when electron propagate in the momentum space from left-hand side to the right-hand side. And this spin flipping behavior from spin-up to the spin-down will correspond to the flow of the sector, spin sector in the feature spectrum, from the spin-up sector to the spin-down sector, and forming a gapless topological boundary state in the feature spectrum. By contrast, if the time reversal symmetry preserved, we find the feature spectrum shows an insulating phase. Meanwhile, the topological boundary state in the band structure is gapless. So this behavior, the gap open on the edge state in the band structure, resulting in the gapless boundary state in the feature spectrum, or the topological boundary state in the band structure is gapless while the feature spectrum remains a gap. This behavior we call the feature energy duality. It means that the total number of gapless topological boundary state in the band structure combined with the gapless boundary state in the feature spectrum equals the spin-Chern number of quantum spin Hall insulator. This result is very important because it shows that the bulk boundary correspondence is still valid. As long as the topological invariant number is not zero, there will correspond to a gapless topological boundary state on the edge of the system. Whether this gapless boundary state will appear in the band structure or in the feature spectrum. So let me provide a very brief summary of these examples. If SZ, spin Z is conserved in the Hamiltonian model, we can perfectly decompose the Bloch wave function into the spin up and the spin down state, and then we can calculate the spin-Chern number from the Bloch wave functions. And in this case, the topological boundary state is gapless in the band structure. However, if we include the Rashba spin orbit coupling and the Zeeman exchange field in the Hamiltonian model, the spin up and the spin down state will mix with each other. So in this case, the spin-Chern number cannot be well divided through the Bloch wave function with the spin basis. And in this case, the original gapless topological boundary state open a gap due to the Zeeman exchange field we put in the Hamiltonian. So in order to redefine the topological invariant number and understand the bulk boundary correspondence, we turn our approach to the feature spectrum topology. Because the feature eigenvalue are still separated into two sectors, we can use the eigenstate of the feature operator to redefine the topological invariant number. And we found in this case, the gapless topological boundary state is not appear in the band structure. It appear in the feature spectrum. So if we follow this idea and extend to the multilayer case, we find that the spin-Chern number in the multilayer Hamiltonian model from the feature eigenstate increase linearly as a function of layers, while the Z2 index from the block wave function oscillate with number of layers. So this result implies that the monolayer K-Mollet model may